Good evening, everybody. Tonight we're going to talk a little bit about rock joints and gold. It's not a rock and roll joint, and it's not a joint. It's a rock joint. So you'll get more in a second about what that's about. Let me check to make sure we got everybody coming through and the audio is going good. Tonight we are going to talk a little bit more about rocks and how they connect to gold. I had a question come from someone in the audience. It was a good one. Basically, they had some pictures they posted to me that were of an area in the desert where there appears to be, you might call it a stack of marshmallows, but these boulders were standing on end, one on top of each other. And the question was, because they're rounded, is this a sign that there was an ancient river, a big one, going through the area? And my answer is a cautious probably not, and I'll explain that in a second. But it's worth the question, and so what it all comes around to is a rock joint. How do you determine whether the rock, the boulder, the rounded thing that you're looking at, was placed there or actually just wore in there? It's a big difference. So, because if it's placed there, that means there's movement of water going through on a huge scale, and therefore there could be a movement of gold through there on a huge scale. If it's simply worn in place, it's a different discussion about its relationship to gold, but it's not because of water flow and erosion in that sense. It's more having to do with how joints and cracks form in the first place and what they look like, so you can kind of spot them, know what you're looking for. So, tonight we're talking about rock joints and gold. I should have a rock and roll theme going right now. Hey, post below if you want me to have theme music when I start this thing up or not. I've had, I've had some stuff in the past. Every time I do it, nobody likes it. Well, some people like it, some people don't. That's the problem with music. But it does add a cue in point where people know, okay, he's coming on, and so I can always do that and go live, It just creates an environmental issue. So I want to see if you like music and would like some music, what kind of music would you like to hear? That's the question. Because PJ's choice isn't always your choice. I might choose Bach, Turner Overdrive. So let's see, we've got 14 people on, and the audio is... There we go. We've got people. So let's see. We've got 14 people on. And awesome. So there we go. And hi, Adam. I want to rock. Yeah, rock and roll those boulders. Bob Sheasley's on from North Carolina. Steve Ford is here. He's in the room. Brian Porkney is here from Michigan. Music is good, he says. Steve Ford says, I'm not worried if you do or don't. So that's kind of where I am. But, we can talk about that. That's okay. Victor Fraser says, I like music. Now, the question is, what kind of music? I know them from Gold Digger. Brian says, The Who. There you go. Now you're getting there. Pink Floyd. Backside of the Moon. I see. We know where we come from. Jim Tripp says, hi from Arizona. Hi, Arizona. Glad you could join us. So, I'm Prospector Jess. This is sourdoughminer.com, huntingforgold.com, and what we're talking about tonight is rock joints and gold. So, specifically, the question that was asked was about seeing a stack of boulders. I don't think I could share that very easily. But anyway, the particular picture he had was a stack of boulders. Envision this. These were, a skyscraper in height out in the California desert. And so the question becomes, well, how did they get there? And the way they appear is kind of a stack of marshmallows, if you will, rounded in nature. Not completely, though. They're a little bit kind of almost cubed. And then they appear out of a pile of sand and debris. We've talked about this before, alluvial stuff. And so what happens is he's got this big fan of material coming down, you can imagine, toward you. And up in the top is this protrusion of these rocks that look like they're just sort of stacked randomly. but not quite. And that's the thing I'm going to talk about tonight, because whenever you see the not quite stacked, as opposed to purely randomly stacked, purely random implies water motion. And especially if the kinds of materials are mixed up, then you know there's been something disturbing this on a grand scale. But if it appears to be maybe tumbled and tossed, but they're the same sort of material in it, you can almost make out, kind of like you can make out of the continents, the outline of one piece fits with the outline of the other piece. You know, a little puzzle fitting here. Well, if you have rocks that are sort of fit together but tipped, then start suspecting jointing, because that's how those rocks come into play. So I'm showing you one right here. Again, tonight we're sponsored by the 2020 Water Flow Sourdough Miner Report. Check that out. Let me go to... So look at this picture right now. What you're seeing is metamorphic material, very weak in its strength, and has a particular tendency to break along a fracture zone, a kind of a cleavage, if you will. And so what you end up with is something that has a lot of blockiness to it, a natural blockiness. And I'm going to paint some colors on this thing just to kind of make it clear, that follows a certain plane or a certain line. So if you look, you see these cracks that go down here, and you see more of them over here, and more of them over here. In fact, all the chunks, these little pieces, they all break off in little blocks. So what I was referring to earlier is whenever you have one of these joints, these fractures, the material will break off and won't necessarily, depending upon its size, in these things, because of the floods that come through, they peel off and head downstream in a hurry. But on a bigger chunk, it might just rock into place and then get ground by everything traveling by it. Hence the rounded marshmallow appearance. Now, in the case of desert, what he was looking at was more of a dacite, not these greenstones, so a harder material. I'll get into that in a second. But that harder material tends to erode slower, and so the end result is, one, you need some water flow to erode it. In the desert, you're not going to get a lot of water flow, but you will get water flow. Primarily in the desert, though, with granites and things like that, they're susceptible to freezing temperatures and what's called, basically cracking by hydraulicking. So this thing will get water down inside the crack, and then as the water freezes, of course it expands 25% and jacks up the piece, and then it freezes again and jacks it up a little further. Okay, and you get this frosting, lifting kind of action that will peel sheets of the material away. As it peels the sheets, they aren't necessarily, as you can see even in this picture, they aren't necessarily straight lines. They kind of follow a sort of straight tendency, but they will have some curvature to them. Now in granite especially, so it tends to peel off in these shells. And you'll see that, like if you look at pictures of Half Dome, I'll get to that in a second. Here we go. But you look at pictures of Half Dome and the area in Yosemite, and you'll see these big shells, and sometimes these things come off, they peel off in sheets. They had one about 3 years ago peeled off. It shot a whole sheet, of which one chunk broke off. It was the size of a small house or an apartment. It went all the way to the valley floor and rolled out. It was, somebody got hurt or killed. It was bad. But the fact is, it's a lot of material, and it's there just sort of being released every year a little bit more, and then pretty soon its mass and the tensile strength of what remains is not strong enough to hold it in place, and bang, away it goes. And those things tend to round things, is what I'm getting at. So those tend to round them off a little bit, and then if there's any flow at all through the area, it will tend to run sand and grit and things like that, especially if it's got quartz, and just sort of sand that stuff smooth after centuries. It doesn't happen in 1 year. It happens over a long period of time. So that's kind of the picture for this. Now what I wanted to do is kind of plop a picture in front of you. So we're looking at, what happens when this stuff breaks free and flows downstream, but also where are these joints and what do they do? Well, they vary based on the kind of rock you're looking at. So I thought I would spend a little bit of time kind of diving in. Neil Young, there we go. Heart of gold. Awesome. Sorry, I was distracted by my cell phone, officer. Oh, that's fun. Yeah, I have a brother-in-law who's a real Neil Young fanatic. That guy's still going at it too. That's pretty amazing stuff. He was also Pink Floyd fanatic too. He was also my best friend in high school, and we spent a lot of time trooping through the Sierra Nevada right in the gold country. So, yep, he and I know that place real well. So let's see. So I'm going to go and show you what I mean. So looking at joint geology, not to be confused with any kind of cannabis pharmacy. This is rocks, and not rock and roll, but rocks. Geology. So we're looking at breaks and fractures of natural origin. Okay, that's the key here. So you have some kind of break or fracture of natural origin in the continuity of a body or a layer of a rock. So if you look at this picture here, see if I can open it up, pop it open, and we can look at it. Notice the layers. Okay, wow, my crazy line drew just about right. Okay, so we got all these layers coming through here and forming these joints. Now notice these joints go kind of horizontally. Notice in the background, this is closer to the marshmallow structures I saw. Notice there are joints both horizontal and vertical here. And that those joints form the cleavage points for these massive boulders. But also notice they're wearing like a marshmallow. They're rounding in the corners. That isn't done because these things were being deposited, stacked one on top of each other in water flow that put it here. No, it's because the water and the aging of these rocks as they freeze over the years peels these things off. And this particular kind of rock and mineral, this stuff down below looks a bit like slate. The stuff up above looks like andesite or yeah, probably andesite. And so what you end up with is this structure very much like granite that has a tendency to crack along these cleavage lines and then peel off sheets or peel off whole chunks, boulders. It'll come downhill. And so it makes a big difference. And this is Kazakhstan, so Russian stuff. Now let's go look at, so close this tool. Back to our joints in geology. So that's two or more intersecting joint set is a joint system. So you can have one crack. Let me get the cracks out of the text. So you can have one crack that consists, basically of, oh boy, drive carefully. So one set of cracks will just form a joint, but intersecting cracks form a joint system. Now, why is that important? Well, because joint systems are what remove whole blocks of material from the rock itself, the base rock. In this case, the base rock is the one in the background is a batholith. This one up here, right there. Not showing so well. Stop driving. So anyway, so that's one kind of joint. Now look at this one over here. These are orthogonal joint sets. They're running perpendicular to each other. This is the kind of thing that you'll see in even weirder ones in basalt. Okay, but you'll see this kind of thing from time to time, and what it also means is these lines will crack in this nice square tile arrangement, and then the pieces will peel off. In this case, the pieces will peel off like you can see right over here. You see these blocks? Okay, well, those blocks peel off. Now, why do you care about joints? So why would you care? Well, you care about joints because two things. One, it's where rocks come from. Big ones. Okay, they break from big rock structures and fall free however they break off from whatever source causes the break off, whether it's a rock slide, earthquake, a flood, and huge floods do this all the time, or it's some other freezing action that releases it, or etc. Okay, even to some degree air, but not so much. People tend to think that all the stuff in the desert is formed by arid action of air and sand and stuff, and it does that, but it does it on a very microscopic scale. It's basically putting a patina on the rock and sanding the finish on the edge. It's not creating these blocks and structures. These are water and earthquakes and landslides and stuff. And so when we look at this particular structure we're looking at here, you can see that crisscross. Well, think of those crisscrosses going very deep. As they go to depth, that becomes a conduit, a weakness for hydrothermal stuff to move up through. Hence, gold, platinum, silver, and nickel, cobalt, our good friend lead, and so forth, copper. And I could go on and on and on. But that's the idea, is it comes up in those fissures. Now it can come up as quartz stringer, or it can come up as a sulfide solution kind of thing, which would plate out as a bunch of oxides or sulfides that would have to be reduced to produce the metals from it. And that's common in copper, for example, malachite. And so you'll see these hydrated or oxidized materials, and then they have to go through a chemical process to reduce the metal. They call it reduction. They're basically taking something that's been oxidized and converting it back to its base metal, and then essentially removing the oxygen or the hydrates from it. And that's a chemical process. The more tricky and the more high temperature, like pyrites, the more expensive and the less profit can be made from those chemical processes. And that's all comes into play in determining what you have. But the key here is this is an opportunity for the fisher essentially to lock in some gold down in there in the right conditions. So two things have to exist. One, the fissure has to exist. And two, the hydrothermal material has to move through a zone that's enriched in metals. Somebody asked the other night about on the question and answer session about the area around Mount Hood not having much gold. Why is that? And why do all volcanoes have gold? And the answer is no. They have to go through an enriched area of material that dissolves into the fluids that move through, so that it can carry that to the surface. And without that enrichment down below, and without the right fluid chemistry going through there, you won't get the intrusive gold that you need from a volcanic activity. Even though there's lots of vents and lots of hydrothermal activity, there may be no gold, because if it doesn't travel through gold areas, it doesn't pick up the gold that goes with it. So that's another point to make. So let's take a look a little further here. This is closer to the thing that I was looking at on his screen. You can kind of see this picture here where we have a bunch of materials cracking and kind of eroding into rounded corners. Notice the rounded corner right here, for example. Let me draw on this thing. So kind of, instead of being at right angles, it's really kind of, kind of sloughed off into a rounded corner. That simply means that you're going to find there's material there, but it's let's go to nope. Yes. So there's material there in this corner over here that has peeled off and made it less jagged. In general, in this case, you can see how jagged these are because it's pretty fresh. And that's pretty typical of what you'll see in areas where you have desert climates and exposed rock jointing. One famous example of rock jointing is Devil's Tower. Massive basalt columns that go up and up and up. And you can see the joints just running from top to bottom, so it looks like a bunch of ribbons and stringers. Well, it's basically a pluton of basalt that was extruded up through into a vent and then now is eroded down, so you can actually see where it cooled, and the cracks along the cooled basalt material form these joints, which are along weaknesses in the rock structure. And they're kind of like crystals, but they're not crystals. They're just weaknesses that happen to exploit in a dimensional way. They happen to go in the same direction, or directional, not dimensional. Does that make sense, everybody? Am I losing you yet? Don't want to lose you. So John Polshek, Southern California here. Okay, good. And Adam says, it looks like decomposing bedrock to me. A lot of these things are what decomposing bedrock is going to look like. And this is also why you want to get your eye tuned. You want to be able to see these things and get your eye tuned to what to look for when you look for it. Because it can be deceiving to go through these and not realize, oh, that's a joint. That's an opportunity. I should look around and see if I see any hydrothermal quartz veins or any kind of any kind of metallic structures, like a lot of rocks with stains along the edge, especially if they're green or they're black. That could tell you something really big is there. But see, the jointing in this one is kind of interesting. It's got a lot of structure to it, and a beanie to boot. There's your basaltic columns. That's probably Devil's Postpile in California. No, that's Turkey. You know, the issue is they sort of look the same no matter where, and that's one of the things about them is they also are an identification tool you can use when you're looking at this kind of structure. You can immediately know it's basalt and it's columnar. What's cool is on the top, if you look at the top of these things, the way they erode, oftentimes a glacier will cut through here on the top, and what you'll find on the top are little octagonal tiles all interlocked together. Fascinating stuff. You kind of have to ask yourself, what in the world is that? Now this is a Mars, okay, so it even happens on Mars. See the basalt structures that are formed here? Let me flip to the full screen version of this. So we're looking at the same kind of structure, basalt, and then we have these talus slopes sweeping away, so they're going out and away from here, away from the mountains, okay, and so forth in the various directions that they would peel away from this material. But notice all of this has these columnar structures. You can see it by the shadow they throw. And so all of a sudden you can identify the rock material as basaltic, or basalt in nature, because it has this massive columnar structure to it, and also because of some of the color that they would sense from various spectrometers. But it's interesting, you know, you can apply this intergalactically. And it's done. There's a whole field called lunar geology. I had a professor who actually planned lunar landings on the Apollo missions. He planned where they would pick up rocks, and we had a rock on campus there at UCSD that was from the moon. Quite valuable. So again, here we go. We got this. Now this has got both cracks and it has that sheeting. Okay, so what we're seeing here is exfoliation, and this is granite gneiss. Okay, so we have a mixture of granite and gneiss. Gneiss is a metamorphic rock, and granite is a igneous rock. And so what you're seeing here are kind of a combination of effects, where this is that exfoliation or sheeting that occurs, and these are those fissures, those big long joint cracks that form through these things. And so that's kind of what you're looking for. Now, in all of these cases in this situation, I haven't seen any of them that show hydrothermal venting taking advantage of these cracks. Now, some of these rocks might have minerals embedded in them that have gold, and so you'd have to be careful to check the detritus, the leftover material afterwards, to see what's in there. Here's a really cool limestone structure that's cracked like that. Let me clear the board. So it has a very interesting, intricate structure that is very unusual. Almost looks like cubes of gems or something. And then look down below. You notice this stuff down here? What do we talk about? Okay. Well, what I see down here are a lot of rounded cobbles. What I see up here are a lot of blocks. And then I see some sheets of stuff here, some more clay kind of silty material. But that doesn't match this stuff at all. So this down here is a big question mark that should be running through your head. How did that get there? I'll bet if you look behind me, you'd see the river. But the rounding tells me it's a river. Okay, that's the key. The fact that these blocks are so chunky right next door tells me that they fall down and probably disintegrate in the very first flood that they get hit with. And only this region through here is it concreted. These things are probably through here like concrete. Very hard. Notice how resistant to wear this particular chunk has been, even though it's right next to all these cobbles that are rounded. That ought to tell you a little bit about its durability. So that's one other kind of situation that can develop. And that's probably it. You know, this is kind of a fracture along sandstone. Sandstone does some pretty weird stuff. It fractures along not quite planes. And so the reason it fractures the way it does has to do with the way the sand and silt was laid down, and can tell you directional flow for the ancient river that was there. It can tell you information galore about how the waters settled in the area, and it could even tell you a little bit about the possibility of fine gold being embedded in this sandstone or siltstone or shale. And so that's the kind of thing you want to keep your eyes out for, is that kind of information. And so that's kind of it for right now. I just wanted to talk and spend a little time talking about these joints because they play a big role in what we're doing when we prospect. And it's important for us to get a good feel for how they fit together with what we're doing and where we're going next. I'm in the wrong screen. I keep trying to turn the screen to the other screen. So that's kind of what we're talking about tonight, is these joints and how they interlock and how those fractures can form fissures for intrusive material to flow into in the way of hydrothermal vents and other kinds of flows like lava and volcanic activity and anything that can exploit those flows. It's a two-way street. Water can go down in there and eventually cause hydrothermal activity to take place because it's coming from the surface and finds a way deep into the surface of the earth. That kind of stuff. So anybody got any questions? I think that's it for tonight. Great show, says Vic Todd from Western Australia. Thanks, Vic. I appreciate that. Oh, boy. Yeah, Steve says it looks like it here in Australia. The funny part is that once you get to know rocks and minerals and gold and minerals and other minerals, you find out very quickly that there's quite a few varieties throughout the earth, but the repetition, the patterns repeat. And so some places it's more rare than others to see things like kimberlites and lamperites, diamond ore. But as people started looking at those closely, for example, they discovered that they had missed a whole bunch of those in, they knew they had a couple here in the States. What they hadn't really focused on heavily was just how many existed in Canada. And so now it's the hot place to be when it comes to diamonds and new finds. It's the ticket. And so that's true of a lot of things, and I'm sure it's true of rare earths, for example. All you need to do is write to your president and write to your senators and congressmen and let them know that we need mining for our security, for our safety, and for our future. And the truth is, because we need things like rare earths, we even need gold. Maybe not as much as one might think. We absolutely need silver. It's used a lot. Platinum, indispensable. The connection of all those together, we've talked about it over and over again. They're all connected at the hip. You can't go looking for silver and not end up looking for gold or platinum. Now, you could look for diamonds and not find the others too much, but they actually have a little bit of a relationship too. So, you can't go excluding one thing because you don't want people to find that stuff and then go for another. The whole thing about gold is, don't disturb the mercury. Well, the mercury's there, whether you like it or not. It's getting disturbed every winter, way more than anybody ever disturbs it. The problem is I cannot pull out rare earths without pulling out and reclaiming all that mercury. That's a good thing. That's a great thing. In fact, the mercury yields money, even if it was just to be deposited in the deepest, darkest vat of salt that you can throw all your radioactive materials in and never be seen again. At least somebody would recover it and it would be eco-friendly. Nobody said anything about that. But that's a fact. We need these products. If we don't have them, we cease being a modern world on a grand scale. So think about that next time somebody tells you don't mess with that crack. So that's rock joints and gold for tonight, and I'm over and out for Prospector Jess. I just want to touch bases with you guys, and yes, we get diamonds here, only small yellow things, says Steve Ford, with the gold. So there you go. And that's true. You should be looking for gemstones when you go look for gold, because they come together. And that's enough of that for tonight. Prospector Jess and rock joints and gold. And what we're looking at tonight is how to figure out how all that fits together and what you can see that tells you about gold. Check out the 2020 prospecting thing I have out there. I sent you that link, and take a look at it. Let me know what you think. Let's see this over here somewhere. There you go. Check that link out. Go try it. If you like it, get it. Catch you then. Good night and good prospecting. Prospector Jess over and out.